Okay, this is going on page 46 when we're done, right? We're going to look at Pascal's triangle and the binomial theorem, right? This should be a little flashback to geometry when you did combinations and permutations, and I'll show you how all this is related here in just a minute. We're going to use it to expand binomials. Binomial has two terms, right? Hence the prefix by there. So expanding expressions in the form a plus b to the nth power can be tedious. Now remember that if I have x plus 3 quantity squared, that is not x squared plus 9, right? It's like x plus 3 times x plus 3, then we expand that, right? Which we should be able to do very, very easily. So let's just do it a piece at a time. If I do FOIL, the first two give me x squared. The outside two give me 3x. The inside two give me 3x. And the last two give me 9, right? Then I clean that up, and I get x squared plus 6x plus 9. Of course, it's totally fine just to go straight to that last step when it's simple like that. No big deal, okay? All right, so then I have x plus 3 cubed, which again, I don't just cube both of them. It becomes x plus 3 times x plus 3 squared. Well, we just found x plus 3 squared right there, right? So I can do x plus 3 times x plus 3 squared, which is x squared plus 6x plus 9. So then to multiply that, I'm going to distribute both of the terms in the first one. So I'm going to take this x and distribute it to all three of these. So x times x squared is x cubed. X times 6x, 6x squared. X times 9, 9x. Then I do the same thing with the 3. 3 times x squared, 3x squared. 3 times 6x, 18x. 3 times 9, 27. Right? Totally doable. Then I clean that up. So I've got x cubed. I used that one. Then I have 6x squared and 3x squared, so that's 9x squared. Then I have 9x and 18x. That's 27x plus 27. So if I add x plus 3 to the fourth, then I'd have to take x plus 3 and multiply it by that, right? And then do it again and do it again. And if I wanted to get all the way to x plus 3 to the seventh, that'd be a lot of multiplying stuff out, right? Totally doable. We are capable of it, but it's very tedious, right? And we wish there was a different way, and there is, okay? So we have what is called the binomial theorem, which it looks crazy, and I know it does. But if I give you the generic form of a polynomial, that looks crazy too, right? But it's really just x squared plus 3x plus 5. I mean, or this is a polynomial, but if I give you that general term or the general form with all the variables and stuff in it, it looks insane and very complicated. Same kind of thing with the binomial theorem. This is what the notation is using combination notation, which has a formula, which we'll talk about. But the good news is we don't have to actually use that formula. But the formula has factorials and stuff in it, again, from geometry. And this would be so like n things taken 0 at a time, n things taken 1 at a time, or whatever. But we have this a and b here. So this was like our x plus 3. And you can see how a and b fill in through here, right? Not a big deal that you actually understand completely what this looks like. It's fine, just showing it to you. So, and it does say at first glance, it may look a little intimidating and complicated, but it's not that bad. Two main things to remember, which will make more sense when we actually do it. But when we expand it, so this is your a and the b, the expression a, whatever that is, as it starts with a degree n, whatever n is, and then it decreases by 1. Whatever b is starts with 0, and it increases by 1. Okay? And it becomes very, very easy to do if you do it in the order that I tell you to do it in and use the little pattern. I do not suggest you try and do any shortcuts here because we're not going to use it enough for you to necessarily remember the shortcuts. I think it's better just to be consistent, and if you can do that, you'll be able to do it every time. It'll be no big deal, okay? So we're going to use Pascal's triangle instead of the formulas and stuff. So we're going to watch a little 4-minute video about Pascal's triangle. Here we go.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle, and in China, it's Yang-Wei's Triangle. To much of the Western world, it's known as Pascal's Triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art. It's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row, so 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics. And it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Okay, so whether you love or hate math, I think you can't deny that that's kind of cool, right? There's a lot of cool patterns in Pascal's triangle, and it's going to keep us from having to do some crazy looking formulas that aren't necessary for what we are doing. So if you look at Pascal's triangle here, some of it anyway, goes on infinitely, The rows start numbering with row 0. 0, 1, 2, 3, and so forth. But if you're actually looking at the rows, if you look at this diagonal here, if you look at this diagonal, which were the natural numbers, this is the row number. So the second number in the row is the row number, okay? That can help you figure that out, so especially so you don't have to count all the way down if you're trying to find a specific row. And each number in the row is called an element. So we start with the 0th element, which is a weird thing to say, but so this is element 0, element 1, 2, 3, 4, 5, 6. So there are 7 numbers, but 6 elements because we start with this 0th one. And the value of n things chosen r at a time. Okay, that's what we're talking about with the combinations, like trying to pick 5 people on a basketball team. Or with the rth element in the nth row. So the good news is we're not going to be, with what we are using this for, we're not really necessarily concerned with the element numbers and things like that. We're going to be looking at these as term numbers because we're going to be expanding binomials, and the counting is a little less weird. But hopefully you understand how it's built. You start adding, right? 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, and 5 plus 10 is 15, and so forth, right? So go ahead and write in row 7. Write in the 7th row. All right. We good on that, how it works? And so if you had to do the 8th row, the 9th row, the 10th row, we could do that, right? I'm pretty confident that you're not going to be asked any questions from like the 23rd row. I mean, I guess it's possible, but I believe that these will be non-calculator questions so that you have to use Pascal's triangle. I don't think that they're going to go nuts with the numbers here, so we'll see what happens. But okay, so let's flip this over. So row 5 is circled, right? In the 5th row, the first number 10, so there's 2 10s. That is the second element, because remember we start with 0. So this, if you see this notation here, it's not a fraction with a missing fraction bar or anything. It's 5 things chosen 2 at a time. Your answer would be 10. That's how you get that number off of there. But again, we're not really looking at this exactly like that. And this is the combination formula that you would have seen in geometry. You did combinations and permutations together. Can anybody tell me the difference between the two? Even if you don't know which is which? Why they were different? Okay, so okay, let's talk about it this way. Let's say that we've got a Little League team, okay? So I looked up some stuff about baseball since the Astros are in the playoffs right now. And I mean, I already knew some of it, but I didn't know anything about Little League and how many players and whatnot. They say on a Little League team, you usually have between 12 and 15 players on there so everybody has a better chance to play. So I just used 12. So let's say that it is T-ball, like the 4 and 5-year-olds, right? If I'm going to figure out which 9 are going out on the field, does it really matter at that point what position you put them in most of the time? No, because none of them have a clue what they're doing, and they don't even understand what's, when they first start, they're no clue, right? So I just need 9 people. I'm just picking 9 people, kind of like the 5 people for the basketball game, right? If I'm not picking positions, I'm just picking you 5 out there, go out and play. So that's just a combination, because I just need 9 people. I'm not putting them in a specific order. So if I had 12 people, and I just want to say, okay, I need to pick 9 people out of there. How many different groups of 9, that's just a combination of 9, could I pick? Okay, so think of a number that you think how many different combinations of 9 I could get from 12 people. Just think of it. You don't have to tell me. I'm not going to ask you. I'm going to tell you what the answer is. I'd have 220 options of my different 9 people, just groups of 9. Okay? Now let's say it's not Little League. Let's say it's the Astros, right? And I've got 9 batters I have to put in a batting lineup. Now, does it matter what order they're in? Absolutely. There's a lot of thought, a lot of science that goes into that. But let's just talk about how many options the coach actually has. Now, I know things, come into play. Obviously, you're going to put your best batter first, all that kind of thing. But, I mean, we can also just think about it as T-ball. You got 9. It really doesn't matter what order they're in, but how many different orders could I have? So of these 9 people, when order matters, who is first, who is second, who is third, how many different orders could I have? That's a permutation when order matters, or if like you're going to line pictures up on a wall, that type of thing. So I want you to think of a number, okay, that you think how many different batting lineups could I make if I didn't really care about ability? Just how many different ways could I line up these 9 people? So just think of a number. I'll give you a second. Then I'm going to tell you what the number is. $362,880. Doesn't that seem insane? Doesn't it seem wrong? It is wrong. I mean, it's not wrong. No, it is not wrong. It does seem wrong. I always have to double check myself because it seems insane. Now, of course, ability and stuff comes into play, but I want you to see how drastically it can change. A lot of teams, especially when Maldonado is catching, we take our batter, our catcher, and he's got the 9th position, right? Dusty may mix up the rest, but Maldi usually stays 9th. God bless him. He can't roam. I don't know how he sits like that. He's got to have bad knees. But if I fix him in the 9th position, then if I want to change up the 1 through 8, here's how many choices I would have then. It's 40,320, and it changes drastically, right? So these numbers and permutations in general don't have anything to do with what we're doing right now. But I'm just trying to remind you of what combinations and permutations were when you were doing them, okay? And in geometry, you probably talked about Pascal's triangle, but the purpose was for you to use these formulas that have the factorials and stuff in them. You can use some buttons on the calculator, and the calculator can do it for you without the factorials, but that's not how these questions are working. We are using Pascal's triangle, non-calculator questions, okay? So let's look at how we're going to make this work. And like I said, if you do this the way I'm showing you every time, you'll get the pattern down and it's going to be no big deal. Yes, you could do it, whatever. I mean, you do what you want, but just trying to give you the best way to make sure that you can do it correctly every time. So if I want to use Pascal's triangle to expand x plus 2 to the 5th, I'm going to go up here and I'm going to look at this 5th row right here. And I know it's the 5th row because it has a 5 right there, right? And because I don't want to have to scroll back and forth, I'm going to write down right here what those numbers are. It was 1, 5, 10, 10, 5? Yeah, 1. Sorry, I had a brain fart. I thought there was something else in there. Okay, so that's the row that I'm looking at, but I just don't want to have to scroll. You don't necessarily have to rewrite it. So here's how we get this to start. Remember, this is A, this is B. Okay? So I'm going to take the first number in the row, which is 1. Then I'm going to multiply it by A and B, in parentheses, x times 2. Okay? Plus, I take the second number, which is 5, multiply it by x times 2. Plus 10 times x times 2. Plus another 10 times x times 2, plus 5 times x times 2, plus 1 times x times 2. Now, we're not done with that row, but do you understand where everything came from right now? Okay? Each of the first numbers comes from Pascal's triangle. The x and the 2 are the same every time. They're coming from what I am actually expanding. Okay? So now, I've got to go back and put some exponents in there. And this is where it said A decreases and B increases, that sort of thing. So this exponent on the x, this is going to the 5th power, so x has a 5 on it. Then it reduces. 4, 3, 2, 1, 0. Then I need an exponent on the 2. We start with 0. Go 1, 2, 3, 4, 5. Okay. What questions do you have at this point? Everybody understand where everything came from? Look at the green and orange numbers in each term. What do the two numbers always add to give you? 5, whatever the power is, okay? All right, everybody good so far? So now we're going to clean it up. When I clean it up, I'm going to look at this term by term. All right, 2 to the 0 power is what? 1, so it's just 1, and that's 1. So really I just have x to the 5th in that first term. Then I have 2 to the, in this one here, I have 2 to the first times 5 is going to give me 10 x to the 4th. Plus, then I look at this one. Oh, goodness gracious. Then I look at this one, and I've got 2 squared, which is 4, times 10, 40x cubed. Yes? Then here, what's 2 cubed? 8. So 8 times 10 is 80. So this gives me 80x squared. Then here, what's 2 to the 4th? 16 times 5, 80, x plus 2 to the 5th, 32. So this is 32. What's x to the 0? 1 times 1 times 1, so that's just 32. All right. Any questions? All right, good deal. So let's look at what happens when we have 2x minus 1, like if we have a subtraction in there, how this is going to look just a little bit different. But we are going to start with, so if I want, I'm going to take this to the 4th power. I'm going to look at the 4th row. What is the 4th row? 1, 4, what? 8, 4, 1? 6, 4, 1. I thought I heard 8. I was like, I didn't think that was it. 6, 4, 1. Okay? And you can write it out if you want to. Again, you don't have to. I just can't scroll in for us to see that. So we're going to start, bless you. I use the first number in Pascal's triangle, which is 1. Then I multiply by 2x and times a negative 1. Super important you're using parentheses here so you're not messing up signs. Plus 4 times 2x times negative 1. Okay, you should be able to finish out writing that on your own. The concept and the pattern, I think, is fairly simple. You just want to make sure you don't leave out a term, that you don't leave out an exponent, something like that. Do I have to write these ones here? Technically, no, but I would, just so you make sure that you have everything in there, like just so that there's no room for error anywhere. All right, everybody good at this point? Okay, so then what exponent goes on this first 2x? 4. And then it goes down from there, right? 3, 2, 1, 0. What exponent goes on the first negative 1? 0. And then we go up. 1, 2, 3, 4. And then you might want to double check that you have, I can see that I'm supposed to have 5 terms because I look at my numbers from Pascal's triangle. I have 5 terms. In each term, the 2 exponents add to give me 4, so I didn't just make a weird mistake there somewhere. And then I am good to go to start simplifying. Okay? Any questions about where anything came from? Yes. Uh-huh. Uh-huh. Right here. That's a diagonal, it's not a row. There you go. Okie dokie. So let's clean this up. All right, so the one inconsequential, right? This -1 to the 0, that's just 1. So really I just have to worry about this. What is 2 to the 4th power? 16. So this is 16x to the 4th. Then in the next one, I have -1 to the 1st power, which is going to make this negative, right? So I've taken care of that. 2 to the 3rd power is what? 8 times 4, 32x cubed. Then I move on to the next one. This -1 squared, that's just going to be a +1. And then what's 2 squared? 4 times 6 is 24x squared. Then when I move on to the next one, -1 cubed is going to give me -1, so that's negative. 2 to the 1st is 2 times 4 is 8x. Then here, -1 to the 4th is a +1. That's a +1, that's a +1, so it's +1. When you have an A minus B situation, the signs on your terms will alternate. Positive, negative, positive, negative, positive, because of the exponents that you have, the even and odd exponents. So that's another thing you might want to check, just to make sure you didn't have a sign error somewhere and you're good to go. Okay? All right, so the bad news is I don't know exactly how this is going to be tested necessarily, whether it would be, to me, I feel like if there's, it might be like one multiple choice question. I don't know that, I mean, I guess it could be on the free response, but I don't know that I would think that. But either way, I don't think that, you may not have to multiply out the entire function, right? We may not have to do the entire expansion. It could be asked something like this, where it just says, what is the coefficient of the term containing x to the 4th when this is expanded, right? So when that is expanded, the first term is going to have x to the 6th in it, right? Something, like I don't know exactly what it is, I don't care. The second term will have x to the 5th. The third term will have x to the 4th, right? If I was going to expand this entire thing, what row am I going to look at? 6. I'd look at row 6, right? So if I go to row 6, the third term is my x to the 4th term. So go up here to row 6. Row 6, third term would be x to the 4th, which means I'd be using that 15, okay? That's how I found that number. So I'm going to use this 15, and then I know I would have times x times 5, because I'm getting that from there, right? The x would have a 4 on it, so what does the 5 have to have on it? 2. Okay. Any questions about where anything came from? How did I get 15? Because if I'm going to expand x plus 5 to the 6th power, I know my first term has x to the 6th, then x to the 5th, then x to the 4th. It's asking me for the x to the 4th term. Since this is going to the 6th power, I go up to the 6th row, and the third term in that row would have the 15 on it. Like if I was to do the whole thing out, then it would be this number right there, but I'm not multiplying out the whole thing. What? Why 15? Because that's the third number. I know that this is the 0th element, but I'm not asking about the element, I'm asking about the term. This would be x to the 6th, x to the 5th, x to the 4th, x cubed, x squared, x, and then just the constant. Okay? So this is when I'm counting the terms, not the elements, okay, because we're counting the terms, it's the third term, because it would be like my third 1, 2, it would be like this term right here. Okay? Does that make sense? We good on that? Okay, so third term, x to the 6th, 5th, 4th, 3rd, 2nd, 1st, 0th, right? So that's where I'm getting the 15 from. We okay with that? Okay, so now I've just got to clean this up. And 5 squared is what? 25. And so it's only asking me for the coefficient, so I don't even need this. I needed to put it in there so I can get all my stuff straight. But I really just need to do 25 times 15, which means I have 15 quarters. You can think of it that way. How much money would you have? What's 15 times 25? What? 375. Okay. All right. What questions you got? Okay, so the next one's asking us kind of the same thing, really, but but the numbers are different here. So I want you to see if you can figure out what number you're taking out of Pascal's triangle. First of all, what row do I look at? 8. Do we have row 8? No, so go right in row 8. No. And then I want you to see if you can figure out what number you're going to get out of that row. What do we want? We want the x cubed term. Okay. Okay, so here's how we can do this. We're taking it to the 8th power, right? So if I'm thinking about exponents, this would be 8, 7, 6, 5, 4, 3. That's the one I want. See how I did that? It's asking me about the x cubed term. I know I start with x to the 8th. 8, 7, 6, 5, 4, 3. Boom, 56. Okay? So I come up here, come back down here rather, and I'm going to have 56 times x times -3, right? What exponent goes on x? 3. So what exponent goes on -3? 5, okay? Tell me something about the coefficient right now. Something you know. It's what? It's going to be negative, okay? That's something you want to focus on. It's going to be negative, so now I don't have to worry about my negative. I know that when I write my answer out, I can say the coefficient is negative something, and I know it's negative because I'm taking a negative to an odd power, okay? So you go ahead and use your crazy good math skills, figure out what 3 to the 5th is, multiply it by 56. 1, 2, 3, go. What? It's 243 to get that. Yeah. Oh, yeah, because 3 times 8 is not 27. It's 24. So you end up with 243 times 56, right? Yeah. With a number like this, I mean, there's a lot of little tricks I do in my head and stuff sometimes, and sometimes I don't trust my head even with those. But with multiplying these two numbers, I would definitely write it down. I know there's probably some of you that can just like look at it and do it in your head, but don't tell us because that makes us mad. Okay. But you should be able to multiply that correctly. Could we multiply this and make some dumb mistake somewhere? Absolutely, myself included, right? I mean, that's what we do. But we're capable of doing it correctly. What is it? Yep. 13,608. And it's negative, so I already put the negative over here so I didn't have to worry about it. Now, let me tell you some things that I know and some things that I don't know about this test and how it's going to be tested. I know for a fact if this was on the AP Calculus test, we could stop right here, and this is what's called a safe stop, and we don't have to multiply it out. I also know that we have been told that the AP Pre-Cal test is not going to be graded the exact same way that the AP Calculus test is. So questions have been raised about, do we have to actually simplify everything out? Do we have to multiply everything out? And I've gotten mixed reactions to those kinds of questions as I've read through things. So I don't know. It's possible that they could say, okay, because what are we testing? Are we testing whether or not you can multiply this, or are we testing the concept, right? We're testing the concept. And so if, this would be fine, but that's another reason why when you write this stuff out, it's very important that you actually write it out where people can read it. Your notation is correct and makes sense. Your parentheses are in the right place, because this might end up being a safe stop in the end. When it's not a safe stop and it really doesn't matter is when it's multiple choice, which is how I feel like this would probably be tested. Like one of these kinds of questions here, and it would be multiple choice, where if it's multiple choice, maybe they'll give you some of those, I don't know, but I would think that you would probably have to multiply it out. I also think that if you did have to multiply it out, to me, I believe that the numbers would be more like this and less like this, because we're not really testing whether or not you can multiply correctly. Does that make sense to you? So don't freak out. I really don't think they're going to ask you something from the 23rd row. They might ask you what the element, I just don't see that with it being a non-calculator part of that. Okay? I don't know if I can. I will try. Just go ahead and go over there. It'll be fine. All right. Any questions? We good? Where's your assignment for today? Delta Math.